So, smart contracts and dApps. You'll hopefully remember, a smart contract is a piece of computer code or a program that is executed within a distributed environment like a blockchain network. All operations and execution results are stored on the blockchain. A smart contract is not a contract between the parties, but a protocol for cooperation. Waves smart contracts come in different forms: smart accounts, smart assets, and dApps. Any Waves account can be converted to a smart account or dApp by applying a special script. The script consists of code written in the right language and contains a set of conditions to allow or reject different types of outgoing transactions. It may also contain some different functions which can be invoked by other users. I hope you remember all of it. In order to make the dApp development process easier for developers, Ride has two types of functions: verifier and callable. So if you follow me here, I will show you some examples of how these functions work. Let's take one of the examples in the online IDE at ide.wavesplatform.com and go through it step by step. In the sidebar of the IDE, you can find script examples here in the library section. We are interested in dApps, so let's find here Ride for dApps directory. And one of the examples is a wallet. Let's open this wallet directory, and there are two files, wallet.ride and wallet.js. Let's open both of them. Great, but I want to note that this editor is read-only, so I'm going to copy the whole content of the script and create a new file with the copy. So now I can modify it and show a bit more than just go through the code step by step. So every Ride script starts usually with directives. But in this case, we see some commands on the top of the script. Here are just two lines, and they just describe that this smart contract, this dApp, just allows us to store some funds on it, so multiple accounts can deposit their funds and safely take them back. User balances are stored in the dApp state, so in the dApp key value storage, as mapping of address and the amount of tokens we store on this contract. Great, now let's move to the meaningful code. Here we have three directives. And every Ride script should start with directives for the compiler. So the first directive is stdlib_version. This directive sets the version of the standard library. The latest version currently in production is 4, but with this example we use 3. The second directive is a content type, which sets the type of the file you're working on. There are two content types, dApp and expression. The dApp type allows us to define functions and finish execution with certain transactions, with certain changes to the blockchain, as well as using annotations. So we can use annotations only if we have content type equals to dApp. Expression type should always return a Boolean value since it's used as a predicate for transaction validation. Expression type is used for smart accounts and smart assets. You can find examples of smart accounts and smart assets in the IDE as well. So here is an example of expression, and this is one statement which should always return a Boolean value. But in our case, we have a dApp with some functions inside it. The third directive is script type, which sets which type of entity we want to attach the script in order to change its behavior. So Ride scripts can be attached to two different entities, either to an account or an asset. If we write a dApp, we can attach it only to an account. So in this case, we do not have a choice. We have to put the script type account here. Right after the directive, we see a callable annotation. Functions with the callable annotation can be invoked by any user, not just the account's owner. In this case, the function is called deposit. You can attach two things to a callable function. We can have some certain data known as arguments and or tokens which act as payment. This function that we are using here doesn't accept any arguments, but requires tokens to be attached. Here are some validations inside the script, so it will throw an error if there are no tokens attached. As a result of the callable function execution, new information can be inserted or updated in the dApps key value data storage. And or funds can be transferred from the dApp balance to the caller or any other address, depending on the dApps logic. Here you can see writeSet function in the write smart contract code. It means that the result of this invocation will be written into the dApps key value storage. This is just like one example of how the callable function can be executed. Another example, here is withdraw function with two results. It stores some data in the key value storage and also transfers tokens. And also we may have functions with only token transfers. So it depends only on the dApp owner. Great. There is also an I variable, as we can see here. We use it pretty often. In parentheses of the callable annotation, we may have different variables. We can call it not only I, but we can call it, for example, inf or invocation or anything, any word that you can use as a variable name. So this I variable contains certain data about a transaction calling this function. So the caller public key, payment details, transaction ID, etc. So we can try to see all the fields of this variable, of this object. We just can type I dot and the ID will show us all available fields like transaction ID, payment fee, asset ID, etc. Great. Also in this example, you can see how to define variables using the let keyword. Here is a variable. And how to check the existence of a given value in a transaction with the extract function and with isDefined function. At this point, you may have many questions about write syntax, so the best way to learn all the basics of write is to read the introduction on GitHub. You can find it on GitHub Waves platform write introduction. If you have struggled to follow me during this explanation and demo, I would suggest doing this right now. The introduction is pretty simple. If you read this text, you'll know almost the whole syntax of write, because write is very simple. So feel free to pause the video and read the document. If you're not struggling, let's continue. I have already mentioned the invoke script transaction several times. You may be wondering how to create that kind of transaction. The Waves Transactions JavaScript library has a special function to work with callable functions by creating invoke script transactions. Let's have a look at an example in the test file. Here we have wallet.test. So we can find here a function, invoke script, and we pass one argument here, object as an argument. The argument contains the dApp address we'd like to call, function name we're going to use, in this case we're going to call the deposit function, and arguments. In our case there are no arguments, so we do not see any arguments here, but we can find another invocation with arguments. Great. Also we have some payment attached to the transaction. In this case we attach Waves tokens because asset ID is null. All other tokens have an asset ID, usually represented by a base 58 string, but Waves asset ID is null, so we can see that this invocation attaches only Waves tokens, not any other token. Great. Also, you can use this invoke script function in the console of the IDE or using Waves transactions library in your client code or in your server-side code using Node.js. So let's look at the second example of the callable function. Let's get back to our write file. Here we have a withdraw function. Here you can see, as I already said, script result, which contains two types of results. We store some data and we transfer tokens. This is very important to remember that now we have two available results of the invocation. In the next versions of write, we will have more results, so please feel free to go to the official documentation and to see what types of results are available now in the write scripts. So here we have some more checks and some more functions we use from the standard library. For example, we try to get the base 58 string from the caller's address. We can do it in this way, like I, as you may remember, contains the information about the current invocation. We can get the caller field of this object, bytes of that caller field, and convert it to base 58 string. Another important point is that if you want to convert something or to use some function, you can do it in another way. You can do it like with postfix syntax, as we call it. It's absolutely the same, but you can write it as you like it more. Here also we have a pattern matching example. I'm not going to talk about pattern matching too much. Feel free to go to the write introduction. It explains what is pattern matching and how we can use it. This is a very powerful tool, and I highly recommend you to read the write introduction document here on the GitHub repository. The logic here is pretty simple. Let's just skim through the logic. With the deposit function, we require that user attach some tokens, and tokens should be only waves, not any other assets. If everything is okay, if attached amount is more than 0, if it's waves, then we update the storage of the dApp and we set the new value for a key. What key? Which key? We will use the caller's address as a key. So as you may remember, we will have in the key value storage, we will have something like this. So that's it. We will just store tokens and we will store some data in the dApp key value storage. What about withdraw function? Withdraw function gets the caller's address, tries to read the data from the storage, like it tries to get how many tokens this user deposited to this account. And if everything is okay, if amount is not more than already stored in the account, then we allow to withdraw. What does it mean? It means that we transfer tokens back to the owner and we update the storage with the new value. So we subtract the amount user wants to withdraw from the storage value. So the logic is pretty simple. I guess you understand all of this. And also we have a verifier function here. So verifier function here is just false. It means that the script cannot be updated. So we lock this account with this script, but we can change its behavior. We can say, for example, that we allow only to, for example, update the script, but nothing else. Let's say that set script transaction is allowed. We will check user's signature. So we will check using sigverify function. We already talked about sigverify. So we'll check the proofs array, the first element of the array, and the public key is the sender public key. And all other cases just false. So if we modify this script like here, then we say that this dApp is updatable, is upgradable, and it requires a signature of the dApp owner to update the code, but all other transactions are not possible to do from this account. Well, here we're almost done with the example and very basic introduction of dApps and callable and verifier functions. This example is a simple demonstration of how some of the functions in Ride work. But I highly recommend that you learn more by playing with some of the other examples in the IDE and by reading the introduction, as suggested earlier. You can find all the relevant links below. See you in next lesson.